In this video, we're going to talk about curve sketching of rational and radical functions. Essentially, the goal of curve sketching is to analyze a function using all the stuff that you know from Algebra 1, 2, pre-cal, and calculus in order to get a really good idea of what that graph of that function is going to look like. So some really important things to solve for are domain and range and any intercepts, asymptotes, symmetry, that could be helpful. And we also want to find the x values for the first and second derivative where it's equal to 0 or it doesn't exist. So that will help us figure out the relative or local extrema, so max and min, and points of inflection, so where that function goes from periods of increasing to decreasing or vice versa. So let's take an example of a rational function. So let's say I have f of x is equal to 2 times the quantity of x squared minus 9 all over the quantity x squared minus 4. The first thing I'm going to do here is I'm going to try to factor this thing and go from there. So I'm able to factor the numerator and the denominator. So the numerator becomes 2 times the quantity of x plus 3 times quantity of x minus 3 all over the quantity of x plus 2 times quantity of x minus 2. So as a refresher, with rational functions, I can analyze so much from the factors that I have here. If I set the numerator equal to 0, that gives me my x-intercepts. So my x-intercepts are at -3 and +3. And if I set the denominator equal to 0, that gives me my vertical asymptotes. So x equals -2 and x equals 2 are my equations for my vertical asymptotes. And another thing to note that if I have the same factor on top and bottom, that's going to create a hole, which I don't have in this situation, but that's good to keep in mind. Now I can plug in 0 for x to find my y-intercepts, and I end up with 1 at 0, 9/2. And I'm going to test for symmetry just to see if this thing is symmetrical to anything. And I do that with the function algebraically by plugging in -x. And when I do that, it returns to me the original function, f of x. So that means that I have an even function, which means that I have symmetry to the y-axis. And another thing that I can do here is look for a horizontal asymptote. So the power on the top n is the same as the power on the bottom m. So that means that I take the coefficient, so a over b, that's 2 over 1. So that means that I have a horizontal asymptote at y equals 2. So looking at this function, I have a pretty good idea of what the graph is actually going to look like. So I first plot my asymptotes, so my vertical ones and my horizontal one, and then I plug in my intercept. So I have one at -3, +3, and then one up here on the y at 9/2. And I know a little bit about rational functions and how they curve around asymptotes. So I've pretty vague idea that it's going to curve like this around these two, and it's going to curve like this around these two asymptotes, and then because the intercept is up here, I'm thinking it's probably going to produce a curve like that. And that helps me analyze what my domain and my range are going to be. So the next couple steps that I need to take is to take the first derivative and then take the second derivative from that. What I've done with this function is I have distributed the 2 on the top to make that 2x squared minus 18, because I think that'll help me out just a little bit when I take the quotient rule. So I'm going to take the first and second derivative and set those equal to 0 to see if I can find any type of critical point. So here's what I get for my first derivative, and when I set it equal to 0, I cross multiply with 0 over 1, and this part zeroes out, so I get 20x is equal to 0. That means that x equals 0 is a critical number. I then take this, using the quotient rule, I find the derivative there, and this is what I get for the second derivative. I set that equal to 0 over 1, cross multiply, and I'm not going to get any real numbers there because it's going to end up that 3x squared plus 4 is equal to 0, and there's no real number that solves for x there. So that means that I'm left with 3 critical numbers. 2 of them are at x equals -2 and at +2. Those are my 2 vertical asymptotes. Those are critical. And then 0 is the one I solved for with my first derivative. And remember, there wasn't a critical number with my second. So that means that if I test all the intervals around these numbers, I get all of these intervals, which is what I'm going to test along with these numbers. I like to make a chart here, and then I start testing stuff and figuring out what it is going to produce. So for my intervals that I have, so from negative infinity to negative 2 to 0, 0 to 2, and then 2 to infinity, I just pick a number in there. And I'm only really testing for the first derivative and the second derivative there. So for example, the first interval here, I might test -5, and if I plug that into my first and second derivative, they're both negative. So that means that the original graph is decreasing and that part of the graph is concave down. And at x equals -2 and also x equals +2, I plug that in, it's undefined, it's a vertical asymptote, we've already established that. And then at x equals 0, another point here, I get 9/2. Remember, that is going to be my y-intercept, and it produces 0 for my first derivative and a positive number for my second derivative. So that means that that's going to be a relative min, because if it zeroes out our first derivative, remember that's a horizontal tangent line. So that's going to be a minimum. And then I test numbers in all of my other intervals, and I find that if I get a negative first derivative, positive second, that means that the original function is decreasing in that interval and it's concave up. And if it's positive first derivative, positive second derivative, it's increasing, concave up. And if I get this positive first derivative and negative second derivative, that means it's increasing and concave down. So here's our final graph of our function for f of x, and we can compare the graph and our characteristics that we have in the chart, and we find that they should match, and they do. So from negative infinity up until that very first vertical asymptote, it's decreasing and concave down. And then from the first asymptote here to our first real critical point, right, our y-intercept at 0,9/2, it is decreasing but concave up, and then it switches to increasing concave up this whole bit. So all of these are accurate. And then from our second vertical asymptote to infinity, that's going to be increasing and concave down. So everything here matched everything here, which is what we're looking for. Now let's look at an example of another rational function. So this time I have a quadratic on the top and a linear factor on the bottom. So just like last time, I'm going to try to factor this thing, and then I'm going to analyze what I can. All right, so first thing I try to do is factor the numerator, but I can't find two numbers that multiply to 4 that add to -2. I throw it into the discriminant, b squared minus 4ac. I get a negative, so that means that I have no real x-intercepts. And then I plug in 0 to find the y-intercept, so that's at 0, -2. I set x minus 2 equal to 0, so I get a vertical asymptote at x equals 2. I notice that for my horizontal, n is 2 and m is 1, so that means that when n is greater than m by 1, it's an oblique asymptote. I need to divide. So I find x plus 0, or y equals x, is my slant or oblique asymptote. And then I try to test for symmetry, and I plug in -x, and it doesn't equal the original f of x function or the negation of the original, so there's no symmetry here. So next I try to see if I can't figure out what the graph is going to look like, relatively speaking, from what I just analyzed. So I throw in my vertical asymptote here, so at x equals 2, my oblique at y equals x, and I have at least one intercept, so that's the y at y equals -2. So I'm thinking that curve will go like this, and the upper curve will go like that, because they're bounded by these two asymptotes. And I'll get to where I get this point in just a moment. So next thing I want to do is take the first derivative, set that equal to 0, and I find 0 and 4 to be two of my critical numbers. So that means that this point right here must be 4, because this 0 takes care of the 0, -2. So if I plug in 4 to my original function, my output is 6. So that's going to be 4, 6, which helps me figure out my 2 points in my range, and my vertical asymptote helps me with my domain there. So now I've got domain and range, critical numbers for my first derivative. Only thing left to do is take my second derivative here, and unfortunately when I set it equal to 0, it zeroes out anything with the x in it as it cross multiplies, so there's no critical number here for the second derivative. And now that leads me into analyzing the test intervals around my critical numbers. So my critical numbers are 0 and 4 from my first derivative, and I have to include my vertical asymptote at x equals 2. So I test all the numbers in and around it. And we can see that when I do plug in 2, I get undefined all the way across. So that's my vertical asymptote. And I'm going to test numbers in between negative infinity and 0, and I get positive first derivative, negative second. So that means that the graph is increasing and concave down there. And that x equals 0 gives me a relative max because it zeroes out my first derivative and it becomes negative for my second. So that is going to be a high point. We call it relative or local, whatever you prefer. And then we test from 0 to 2, and both derivatives are negative, so that's decreasing concave down. We talked about the vertical asymptote, so from 2 to 4, I get negative first derivative, positive second. That's decreasing, but concave up. And then at x equals 4, that's that lovely relative min point, and it's a minimum because it returns a value here. It's 0 for your first derivative and positive for the second, so that's going to be a relative minimum or a local minimum. And then our last interval is between 4 and infinity, and the first and second derivatives both create positive outcomes. And that's going to mean an increasing function that's concave up at that point. And here's two different visuals of the same graph. This one has our relative min and max, but it's missing our slant asymptote. And this one has the slant asymptote, but no relative min and max. So these are the critical elements of this graph that we care about. And now let's switch gears to radical functions. So let's say I have this function here, x over the square root of the quantity x squared plus 2. So let's analyze what we can and figure out what the graph's going to look like. So the first thing that I do here is I try to find my intercepts. So I set f of x equal to 0, and I solve for the x-intercept is 0, 0, so that's the origin, which also means that my y-intercept is going to be at 0, 0, because I can also do that by plugging in 0 for x, and I really just get 0 over rad 2. So I only have one intercept. It's both my x and y at the origin. And then I think, all right, do I have a vertical asymptote here? So a radical in the denominator, that can't be 0, and also a radical has to be greater than or equal to 0. So when you put those two ideas together, it's just x squared plus 2 has to be greater than 0, can't be equal to. So that gives me x squared is greater than negative 2, which, as we know, when we square a number, has to be greater than a negative. So there is no restriction, there's no vertical asymptote here. And then I think about my horizontal asymptote. And because technically this is a rational function, I've got a fraction and a variable in the denominator, although it's under a radical, that's okay. I treat it with an n and over m rule, so this is a degree of 1, and if I take the square root of x squared, that also gives me 1, so they match, and so I take the coefficient here, so that's 1, and that's the square root of 1, but we have to include the positive negative, because when you take the square root, you have to include positive and negative. So that gives me two horizontal asymptotes, one at y equals 1 and one at y equals negative 1. So I've graphed what I know. I have my two horizontal asymptotes. I have my origin intercept right here, and I'm thinking it's probably going to curve up and go like this. I've seen a couple of these before, so that's how I know the curve is going to go, but at least I can put in my two asymptotes and my 1 point there. And so that gives me my domain and range pretty easily. So the next thing I'm going to do is take the derivative, set that equal to 0. So I do that, and there's no number for x there because 2 equals 0 is not a thing. And so I take my second derivative, and I'm able to solve for one critical number, and that is 0. So that tells me that that's probably going to be a turning point or a point of inflection. So what I'm able to do is take my one critical number at 0 and then test intervals to the left and right of that number. So much like the other two examples, we're going to plug in some numbers in between negative infinity and 0, and I get my first and second derivatives to be positive, so that's an increase in concave up graph, and 0 is my point of inflection because it gives me 0, 0, but the first derivative is positive and the second derivative is 0, so that tells me it's an inflection point. So it's going to go from increasing to increasing, interestingly enough, but the concavity is different. So I go from increasing concave up to increasing concave down. And that actually matches the official graph of this, which I guessed correctly, that it's going to go like this and then up. Point of inflection, two asymptotes, and there you go. And one more function to analyze. So let's take another radical function here. So this actually isn't rational because there is no denominator with a variable in it here, so that means I'm not going to have any asymptotes. But let's see what I can find out. So what I'm going to do first is factor out an x to the 4/3 because that's my lowest common power right here. So that leaves me with 2x to the 1/3 minus 5 on the inside, all being multiplied by that x to the 4/3. So I find my x-intercepts at 0, 0 and 125 over 8, 0 because I can set both of these equal to 0, solve for x. And my y-intercept is 0, 0. And there are no asymptotes. So lacking those asymptotes and really only having 2 intercepts, this is all I've got right now. And I do happen to know that the domain is not restricted. There's no asymptotes, horizontal or vertical, so I know that both domain and range are going to be all real numbers, but that's really what I have at this point. So that means I'm going to need to take the first and second derivative. And when I do that, I find 3 different critical numbers. For the first derivative, I find 0 and 8. And in the second one, I find 0 again and 1. So those are likely inflection points that will help me figure out how this thing curves around those 2 points right there. So this is my next step. I'm going to take my critical numbers 0, 1, and 8 from my first and second derivatives. I'm going to test those numbers, including the intervals around those numbers, and I'm going to throw them into a chart like I have been this whole video. And so from negative infinity up until 0, I get a positive first derivative, negative second derivative. So that means that that function is increasing but concave down. And then at x equals 0, that's a relative max because the first derivative is 0 and the second is actually undefined. And then from 0 to 1, I get a negative first and second derivative, so that's decreasing concave down. And then at x equals 1, that's going to be a point of inflection where my first derivative is negative, but my second derivative is 0. And so that's likely going to continue to be decreasing because on the left and right hand side of 1, they're decreasing, but it goes from concave down to concave up. So at 1 to 8, that's decreasing concave up. And then at another point, a critical number, at 8, I get a 0 first derivative and a positive second derivative. So that's a relative min. And then our last interval is going to be from 8 to infinity, and both derivatives there are positive, so that's increasing concave up. So putting that chart into action, I get this more fulfilling and actually filled in graph here. So I have my 2 intercepts, which is all I had before I took the derivatives, and I noticed that I'm going to be increasing here and it's going to be concave down, and then it's going to turn to be decreasing at 0, 0 and still be concave down here. But then at this inflection point at x equals 1, it's going to still decrease but become concave up. And at x equals 8, another point that's important, which is a relative or local min, this thing is going to change to be from decreasing concave up to increasing concave up. And then it's going to hit through that intercept right there and keep on going. So that confirms that my domain and range are going to be negative infinity to infinity or all real numbers as well. All right, and that's going to do it for this video. Thanks for watching.